Have you ever tried running a multiple regression, say, on your company's financial data, only to get, weird results? Like you dump in all of the numbers, total cost, fixed cost, variable cost, production units, for example, and the model spits out something weird, like negative fixed cost? Or maybe your rent goes negative just because you make more widgets. Well, welcome to the world of multicollinearity, the sneaky little monster hiding in your data. Well, what is multicollinearity? Multicollinearity is a statistical phenomenon that occurs when two or more independent variables or predictors in a multiple regression model are highly correlated with each other. This means that the predictors share a strong linear relationship, making it difficult to determine the individual effect of each variable on the dependent variable. This might happen especially if the data analyst doing the regression does not have any expertise in the underlying business, aka domain expertise, to understand the underlying data, which means the variables are just all meaningless numbers to the analyst, something to play modeling with in a vacuum, which is always dangerous since the analyst might just throw everything in the regression soup and just hope for the best. Now, this is seldom a good idea because when you throw in all the variables together indiscriminately, the model can get confused when there are linked or tied together variables somehow. It's like trying to figure out how much each ingredient in a cake contributed to the total calories when some of them are already added together. For example, you throw in total cost, fixed cost, and variable cost into your regression model to predict, let's say, profit, but fixed costs and variable costs are already added up together in total cost, and yet you put them all into the soup. Or you might be tracking marketing spend, which also covers ad spend and social media spend, etc. But you still put everything in the soup and do the regression blindly. After all, you might be thinking, more data, better model. The procedure will sort these things out, right? Well, sorry, not really. Here's a made up example to illustrate the point, just for illustration purposes to see the problems you might encounter if you don't have any idea at all what the variables are all about and you're just trying to regress them blindly. So here's the data, and here's the regression output. So you smile with so much confidence since you've just slayed this problem, given the high R squared, wow. And the ANOVA table, wow, that tells you the model is significant. Except that an inspection of the p-values of your coefficients, well, that tells you none of them are significant. Well, that's weird. So the model is significant, but each of the coefficient in the regression is insignificant. What's happening? And then you vaguely remember that lesson about multicollinearity. So you get the correlation matrix and you get the following. And you also get the charts of the correlations like so. Uh-oh, they look highly correlated with each other. Now this looks bad if you remember your lesson about multicollinearity. This is happening likely because the variables are really related, like maybe variables 2 and 3 suspiciously look like they might add up to track variable 1 more or less. So perhaps they are linked or are subparts of variable 1. So there can be really no clear separation since they are intrinsically linked. So you suspect that to yourself. Then you have a flash of wisdom. Maybe if they're all related to each other, maybe you should just pick 1 or 2 x's and regress against y, right? But the problem is which one? Well, whatever it is, you are already coming to the idea of dimensionality reduction. Because clearly, putting all the variables in the soup just because they're available for regression does not work here. We'll get to that shortly. So, how do we untangle this mess and resolve the problem of multicollinearity and do the multiple regression properly? We'll give you 6 tips, so listen up. Tip number 1, be smart about your variables. If you're not a subject matter expert, get up to speed quickly, or better yet, get somebody who is, to help you figure out the underlying data first. Don't regress blindly except perhaps as an exploratory procedure. Tip number 2, drop variables. Don't throw in everything. If total cost is made up of fixed costs and variable costs, choose what matters. Maybe keep fixed costs and variable costs and drop total cost, or vice versa. Tip number 3, combine variables. Sometimes it makes sense to add things together, like creating a total operating expense from admin costs and marketing costs to reduce the number of variables involved. Tip number 4, Reduce dimensionality via unsupervised machine learning procedures. And this is where the magic happens. What if you could take all these correlated variables and shrink them down to the most important patterns without the confusion? Well, that's where we'll get into the cool stuff of dimensionality reduction. In the future, we'll use techniques like principal components analysis via unsupervised machine learning to take your tangled web of variables and turn them into a simpler, clearer picture. We'll tackle that separately in the near future. Tip number 5. Make your mistakes fast, but learn even faster. There'll always be a concern of overfitting and doing so many other things wrong, so you can be stricken by analysis paralysis. In this case, it's better to have quick results, doing things fast, and then learning from your mistakes faster while minimizing the potential damages. How? Well, you just show the domain experts your results and get their inputs and be open to corrections. They might be able to quickly eyeball spotty results and direct you to better ways to model, which can count a lot more than over-analysis and forever second-guessing yourself. In my own work, I used to do this a lot. If I'm not the domain expert in the model I'm training, I try to spit out a quick result and then I show the result immediately to the domain experts and they'll tell me why or why not my model might make sense. And then I just do it all over again until I get something workable. So I suggest this is something that you can do. Tip number 6. Don't use all your data in one go. Well, this is separate from using all variables in one go. This means having a separate training data to do the modeling and a testing data where your model results can be tested for accuracy, like maybe an 80-20% cut between training data and testing data, where the training data trains the model and you can test for accuracy by applying the model and the test data to see how accurate you are, or test against actual results as you move through time. That can also be done. In the real world, there are no brownie points for elegance or statistical rigor. What matters is accuracy. So let accuracy of prediction be your best guide rather than the statistical rigor or academic modeling. If your model can consistently beat dumb guesses, then it's no good no matter how fancy your model is. In that case, maybe the outcomes are really random. Who knows? This should be at the back of your head always, even while you're trying to improve your modeling. So going back to the problem, given the very high correlation of the variables, perhaps you just do all bivariate regressions possible and choose the one with the best regression results. Well, that can be done. For example, you might have the following best regressions a result after doing all the bivariate cases. So x1 versus y, or x4 versus y. Additionally, there are software programs out there like SPSS that can do what's called stepwise regression, where it will mix up the variables around systematically until it comes up with the optimum variables to include in the final regression. So next time you're working with data, don't just throw everything into a regression model. Watch for multicollinearity, think carefully about your variables, and well, stay tuned for our next video. We'll decode eigenvectors, eigenvalues, and how they help us find the hidden patterns in your data. Hit that like button if this helped you, subscribe for more data detective stories, and drop a comment if you've ever faced the multicollinearity monster in your own projects. See you next time.